All right, so as you're looking at the review problems because you already know how to do them for these mole conversion calculations. And we're going to be looking at a few more mole calculations today. Adding on to it before we get to the wonderful realm of stoichiometry. Stoichiometry is the mole math that involves the chemical reactions. So, on the mole map here, you already know a couple of these conversions because we've gone over molar mass. The mass equals 1 mole. We've gone over representative particles, where that's Avogadro's number, 6.02 times 10 to the 23rd equals 1 mole. Before we continue, what are the types of representative particles out there? Yes?
Formula.
Formula units, good. Formula units applies to which particular set? Which kind of chemical compounds does it apply to?
Particles.
What? Ionic compounds.
Ionic compounds.
Ionic compounds have formula units. Now, what's another type of representative particle? Ions, good, of course, which represent charged atoms that have gained or lost electrons. Very good. I heard another one out there. He said atoms. Atoms, of course, is the name that you would slap on the element. Okay? It's just an element. And then I heard the last one, which is molecules. And molecules we use for what type of compounds? Covalent compounds, where they're sharing. Or if it's a molecule, it's just sharing electrons. Very good. Now, the third one, which we're going to go over later today, is the conversion for the volume of any gas at standard temperature pressure. But we're going to review first before we get to that molar volume. This is the mole map that's on your paper, but it's just as helpful, a little less busy than the previous mole map, but you can refer to either. And yes, you are responsible for knowing your 6.02 times 10 to the 23rd and your 22.4 liters when we get to that one. And then, of course, calculating the molar mass of any substance using the periodic table. Now, let's go over the review here. How many conversion steps is this one going to take? 1. How do we know that? It's just moles and grams here, so we know it's just going to take one easy step. 64.3 grams, calcium fluoride, molar mass, 78.08 grams. Is that what you got? Yeah. Because we're all rounding to 2 decimal places, so we all have the same molar masses here. That equals 1 mole. So, what did you get and how many significant figures should we keep? 3, because our initial measured value, our value here is 64.3 grams, so we need to keep 3 in our answer. So what was the answer? And this would be moles, CaF₂. Very good. Which happens to be correct. Now, next one. This one involves starting with formula units and going to grams. So the word mole's not up there. We know how many steps at least is when you take this. At least 2. So, starting with our formula units, our given information goes in the upper left corner. And when we're using representative particles, the conversion number is good. 6.02 times 10 to the 23rd Avogadro's number. And that equals 1 mole of my substance here. Now, we're going to go from the mole to what? To grams. So we're going to diagonal down that mole. Send it down here to get canceled out now. And we're going to put our 78.08 grams on top. And how many significant figures will we keep for this one? 3, because the measured value has 3. So what is your answer? 686 grams. Calcium fluoride, very good. Which happens to be correct. Now for a little bit more of a challenge problem. Because here, we have to find moles of a sample of calcium fluoride where it's telling us it contains 2.29 times 10 to the 25th fluoride ions. So we have to start with the fluoride ions and work our way to moles. How many steps should this take you then?
3, 4.
3, 4?
Several.
Several. Okay, well let's see how long it's going to take us to get there. So we're going to start with our given information, our 2.29 times 10 to the 25th fluoride ions. And I need to figure out how many that means for my formula unit here and get to my formula unit. So if I'm looking at my fluoride ions, how many are in my formula unit of my, one formula unit of my calcium fluoride?
2.
There are 2 fluoride ions in one formula unit of calcium fluoride, so I put that there. Now that I'm to my formula units, what number can I use?
The mole number.
That mole number, which is Avogadro's number, 6.02 times 10 to the 23rd. Formula units of calcium fluoride equals 1 mole calcium fluoride. So this one only took us 2 steps to get to moles. Now if we had to go further to grams or something, it would be an additional conversion step. So how many moles of calcium fluoride are from those fluoride ions? What did you get? Anyone? How many significant figures? 3. We need 3 from our measured value here. So, what do we get for our actual number of moles? 19.0 moles. Good. And I believe you are correct. Very good. Awesome. Now, so that was the review of the previous mole conversions we have done. Now we're going to look at molar volume. Molar volume goes with Avogadro's hypothesis. States that equal volumes of gases at the same temperature and pressure contain equal number of particles, or equal moles. Now this is true, and this is a gas law. We're going to get to gas laws later and explain more in depth, Avogadro's law. But it's useful because at standard temperature pressure, which is 0 degrees Celsius in 1 atmosphere, 0 degrees Celsius, the reference point is the freezing melting point of water. Does anybody have any idea where the 1 atmosphere might come from? What's that reference point? Yes, what does 1 ATM mean? It means the pressure of the atmosphere where?
At sea level.
At sea level. Very good. That's the reference point. So there are different, of course, pressures from the atmosphere if you're at different elevations, but at sea level it equals 1 atmosphere. We're very close to sea level here, so obviously ours is very close to 1 atmosphere. We are a little bit above sea level though, by the way, just so you know. Now, at STP, standard temperature pressure, 1 mole of representative particles of any gas occupies a volume of 22.4 liters. So that's why we call the molar volume equivalent value is 22.4 liters. Now later on when we get to gas laws, we will show you how that 22.4 number is derived. But for right now, you just need to know that any gas at standard temperature pressure is going to equal 22.4 liters. So that's the magic volume number. So let's do a couple problems with volume. So at standard temperature pressure, a balloon contains 30.2 liters of oxygen gas. How many moles are in the balloon? How many steps is this going to take you? Conversion steps. Only 1. Very simple. Let's go ahead and do that. 0.35 is correct. We have 3 significant figures here. And yes, we are correct. Very good. Now let's look at this second example. One times 10 to the 24 molecules of oxygen at STP. So yes, we're going to have to go to moles first. This is a two-stepper. So we have 9.21 times 10 to the 24th. Now I'm going to abbreviate molecules MLCS because we can't really use moles because that looks like moles. So this is molecules of O2. So what number do I put down here, these molecules? This is going to be Avogadro's number, good, 6.02 times 10 to the 23rd. To get rid of it, we're going to go to moles of O2. Now we want to change and put our moles down here to go to what? The liters of O2. So that's the 22.4 goes there, and the 1 goes down on the bottom. Now everything's going to cancel. And we're left with our liters. So how many liters is that going to end up being? Yeah, that's supposed to be 24. I don't know if I wrote that wrong. That's supposed to be 24. There you go. Correct. What? Are you kidding me? Hold on a second. All right, so then we end up getting 342. 2 or 3? Is it round to 3? It rounds to 3. All right. And yes, I think that was the intention. It's supposed to be 24 times 7/24, so we get 343 liters of oxygen. All right, now let's go with molar concentration here. Molar concentration. Now, we are going to be looking at stuff in solution when we do our reactions lab, so we kind of have to know what concentration means and how to calculate with it. So, the number of moles of a substance in 1 liter of solution. So when you see that like copper sulfate solution where it's a blue liquid, or you saw the cobalt sulfate where it was like that red liquid, that is a solution that has a certain amount of particles dissolved in the water. So molar concentration is how many particles are actually dissolved in there. And it's moles per liter. It has this formula. Molarity is our measurement of concentration we use in chemistry. Moles of solid over liters of solution, so moles per liter. Note, this is the big note here. You must realize that in these problems, they don't always give you moles. They don't always give you liters. Instead, they might give you grams or milliliters, where you have to convert them first before you can plug it into the equation. And I'm also going to show you how to use dimensional analysis to keep it all together so that you don't even really have to stop and calculate in between. So, let's start looking at some examples. And this one shows you a nice diagram too to show you the particles of the solute being dissolved amongst the solvent, or in this case, most of our solutions are going to be made out of water as the solvent, the liters of solution. This one's talking about how when you add, you keep adding it, you can see the color getting darker. If it's a colored solution, the color that's more dark is going to be more concentrated and have more particles in it. The other diagram just kind of shows you one that would be considered concentrated versus one that would be considered dilute, where there is less particles per amount of water. So that's really what we're looking at here. And you're going to be using solutions in the reactions lab, so definitely need to know what concentration means. All right, so this is the molarity of 43.9 moles of CaF₂ dissolved in 1.25 liters of solution. So this one hard or easy? Super easy because they gave us moles, they gave us liters, all you have to do is what? Divide. This one's easy. So we do molarity, moles per liter, so 43.9 over. And what do we get for our value? 30 what? Or 35.1 sounds about right. And you would put a big M here. Or, if you like derived units, you can use the big M, or you could write it as moles per liter, like that. It's like density, where with certain grams per milliliter or something like that. This is a derived unit, it's moles over liter. Hey, we were right, 35.1 molar calcium fluoride, or 35.1 moles per liter of calcium fluoride. Now, both have to be converted here. And the mole conversion, we need molar mass to change it to moles, so that's a little bit more. So let's go ahead and set that up first, and I'm going to kind of show you a little trick here. And we diagonal down our grams, and we're going to go to moles. And we already calculated this molar mass, right? So we already know this one. It's 78.08, yep. All right, so we're going to change that to moles. But I'm going to also deal with my volume here. How many milliliters equals 1 liter? 1,000 milliliters equals 1 liter. So really, what do I do with my 375? I divide it by 1,000, right? But essentially, when I divide it by 1,000, yeah, that's moving it 1, 2, 3 to the left. Change that to liters, like so. 3 decimals to the left. Easy enough? Now, instead of keeping it out of our nice T-chart, guess where we can stick it? If we put it there, guess what? The grams cancel. And what are we left with? Moles per liter. Isn't that kind of cool? And then we can calculate it in all one big calculation in our calculator. And you let me know, what do we get for this answer? And we got what? 1.08, good, and you can write it as M or moles per liter. Definitely correct. Big M means moles per liter. Determine the final volume in which 4.67 moles of lithium sulfite were dissolved to make a 3.89 molar solution. All right, our molarity equation here. What do we have? What do we have? We have the molarity, the big M, and we have the moles, right? So what's missing? Liters. So you can just plug it in like so. Do it this way. Over X liters, right? That's what we're missing. That's one way to do it. And yes, you can shuffle your variable around and solve for X. The other way to do it is the dimensional analysis way. And this is a neat little extra trick when you want to not have to stop and recalculate things, and you can just keep going through the rest of the stoichiometry, which we're going to get to later. If I have moles, I can make that by given information. Now, typically typically, what do we diagonal down when we set it up as a t-shirt? The moles. The moles go down here. Good. And guess what this 3.89 M means? That means 3.89 moles over 1 liter. So I can use that as a conversion factor. That means I can put my 3.89 on the bottom, put my 1 liter on the top. And if I needed to keep calculating through the rest of the reaction, then I could keep going. Either way, you're still dividing here. If you use the formula or if you use the dimensional analysis way. What did you get for your answer? 0.20 liters is correct. Yes, question?
Didn't you just multiply L on both sides, like algebra?
Well, yes. I don't multiply L on both sides. Instead, you know what I do? I switch these. Because that's what multiplying L on both sides is going to do. Okay. But that's extra work. I just flip them. Oops. Wrong one here. All right. Let's look here. How many grams were dissolved in 525 milliliters to make 0.85 molar of calcium chloride solution? Well, you can do it the formula way, but you're going to have to break it up because you have to change your moles into grams. So we can set it up that way. What else do we need to convert right now? With 3 decimal places over to the left. Let's go. Good, let's do that. Now, formula way. That's fine, we can do it this way to start off with. But maybe I will sell you on doing it dimensional analysis. X moles over liters. Now that's going to calculate moles, but you don't want to round here. You want to reach the end. So we get the moles by multiplying our 0.525 by our 0.85, right? That gives us this number. Like I said, we don't really want to round yet. This is the moles. We need to change this over into grams. So 1 mole, CaF₂, once again is 78.08 grams. Right? And what do we get? So that's going to be 35 grams. CaF₂, right? That's one way. Or, you set it up dimensional analysis way, use the molarity as the conversion factor. In this case, if we're going to do it dimensional analysis way, we would start with our volume. Diagonal down the volume, 1 liter equals 0.85 moles. Then we keep going. We stick our moles in here. 1 mole equals the 78.08 grams. And guess what answer you're still going to get? That 35 grams. So whichever way your brain works, you're welcome to use either method. Just